Hello physics students, it's Mr. Dillick. Again, this is a video, I'm going to combine the videos for 4 and 5 into one video here for the sake of time. They're really both about acceleration, which is a new physics quantity that we really need to talk about. At this point we've talked about how to identify the difference between distance and displacement, a scalar and vector version of measuring a change in position on a number line. We've spent quite a bit of time talking about rates, specifically the change in position over time, which for a scalar version is speed, and for a vector version is velocity. But now we want to look at a different rate. We want to look at the concept of acceleration in a little more detail. And it makes sense to talk about this because we just got done talking about graphing, and when you consider that the slope of the line on a graph tells you something pretty important. For the slope of a line on a position time graph, it tells you velocity, and the slope of a line on a velocity time graph, it tells you acceleration. We really need to explore this idea of acceleration a little bit better. So let's just kind of say, all right, we know that acceleration is another type of a rate because you're looking at the change in something over time. But acceleration specifically measures a change in velocity over time. And notice this is there is no version here for acceleration as a change in speed over time. Velocity is a vector, acceleration is a vector, acceleration is a rate. Because we're comparing specifically the change in one thing, of the change in a rate over time. And so it's a rate of a rate, if you will. So this is kind of an interesting idea. Acceleration is one of the toughest ideas, I think, for physics students to learn early on because it means something different kind of to the average person than it does to a physicist. Acceleration to the average person on the street means to speed up, and that's it. But to a physicist, it certainly can mean speeding up, but it could also mean slowing down, and it could also mean changing direction. So if you were in your car and I said hit the accelerator, you really have quite a few choices. You could hit the accelerator that causes you to speed up, you could hit the accelerator that causes you to slow down, or you could turn or apply force to the accelerator that causes you to change direction. So any of those would be considered acceleration. You really need to pull the term deceleration out of your vocabulary for physics purposes. I don't like the term to decelerate because it implies that we need this other word for meaning slowing down, when really to accelerate is to speed up. If you slow down, you're accelerating. If you change direction, you're accelerating. All of those are accelerations. Remember, these are vectors, so when you're talking about acceleration, you have to have a direction that acceleration is acting in. And the most obvious directions on a number line are going to be accelerating in the positive direction, which for our 3 frames of reference in space we talked about might be to the right or up or forward, or you could be accelerating in the negative direction, accelerating to the left or down or backward. And those would be negative accelerations, and that causes a bit of a problem for people because negative acceleration is what people generally call deceleration, and I don't want you using that term. To accelerate in the negative direction is a negative acceleration. So if something is pushing or pulling an object to the left or downward or backward, that's a negative acceleration. If it's pushing or pulling something to the right or up or forward, that's a positive acceleration. Now, what would it look like if we graphed these? Well, remember what we said was that on a position time graph, curves have changing slopes, and they would therefore indicate changing velocities, which is the definition of acceleration. So we'd be looking for curves on a position time graph, like so. So you can see here I drew a position time graph, and I have an upward opening parabola. Anytime you see parabolas, whether they be upward opening or downward opening, or maybe a by the root, like a square root, sideward opening, rightward opening parabola, that means you're definitely looking at an acceleration because the slope here is changing over time. Changing slopes mean changing velocities, and changing velocity means acceleration. The standard unit of acceleration is meters per second, or more specifically, meters per second squared is what we generally call that. But really, we're saying every second that passes, by how much does the velocity in meters per second change? So how many changes in meters per second per second? The equation for acceleration is then going to be a change in velocity over time. And I happen to be writing it in terms of x, but we could simply write this in terms of y or z as well. Keep in mind that a change in velocity is going to be the final velocity minus initial velocity, and a change in time, this is really average acceleration, would be a final time minus initial time. So I should really have a bar over that. Because I have a distinct long time interval, long enough that I have two distinct times, instance and time, means that we're talking about an average. Okay? So a little more about acceleration. We're on to video 5 now here, kind of combining these together. We know that acceleration is a rate. We know that it's a change in velocity, but is there more to it? Well, don't forget, if you're looking at a position time graph, you're looking at curves. You're going to see curves on a position time graph mean acceleration. But what if you're looking at a velocity time graph? What does the slope of a velocity time graph tell you again? That's right, acceleration. So if we look at a velocity time graph and we see that we have anything other than a horizontal line here, then we definitely are going to have acceleration, like this. So I've included 3 different objects on the same graph. And let's talk about the blue line first. The blue line represents an object that is moving, and it starts out, remember this is 0 velocity, so anytime that you're here and touching this line or crossing this line, you could be stopping or even changing direction. And so when we look at this, we can say, all right, this blue one, its initial velocity is positive, and this is x, so that means it starts out moving to the right, but it's getting closer and closer in velocity to 0. So it slows down and actually stops there, and now it drops down into this negative quadrant. So here we can see it's actually moving to the left, and its final velocity is moving to the left. The fact that this is a line, and lines have constant slope, tells me that it's experiencing a constant negative acceleration. So it started out with a positive velocity and slowed down, stopped, and sped up because it was constantly being pushed or pulled in the negative direction to the left. Meanwhile, here this red line is something that started from rest and was constantly pushed or pulled to the right because we have a positive slope. And so that means it has a positive acceleration. Here we have no slope at all, so we have something that's moving at a constant velocity. It happens to be a constant negative velocity. So it was moving to the left, and it's still moving to the left, and it's not changing speeds. It's not speeding up, slowing down, or changing direction. Those are the definition of acceleration, so it's not accelerating. So again, I mentioned this quite a few times now. So what causes acceleration? Accelerations are caused by forces, and I'm going to have more to say about that later. But for now, just keep in mind that things don't change velocity unless something is pushing or pulling on them to make that happen. Forces cause accelerations. If it's a constant force, like gravity, never changes direction, it's always down, always with the same amount of oomph, then you get a constant acceleration, which is going to give you a graph like this, where you have a constant acceleration. On a velocity time graph, it's going to give you a line. If you have a non-constant force that's more complex, you're going to get a curve on that velocity time graph, and that's just not something I'm going to ask you right now. One of the most important things that you can do is think about the question, how can I tell if something is going to speed up or slow down or keep moving at a constant velocity? And so there's a really good table in your text on page 51 in your text. And pretty much what it says is anytime that the velocity is in a positive direction and the acceleration is also in the positive direction, you're going to get an object that speeds up. And if you have something that has a velocity in the negative direction and its acceleration is also in the negative direction, it's going to speed up. If you get a positive and a positive, a negative and a negative, if those two signs are the same, the object's going to speed up. Why? Because we're saying that something is moving to the right if it has a positive velocity and being pushed or pulled to the right. And if you push or pull something in the direction it's already going, it's going to speed up. On the other hand, if something's moving to the right, a positive direction, and gets pulled to the left or pushed to the left, it's going to slow down. So is it possible that something could have a negative acceleration and still speed up? And the answer is yes. If it was already moving in a negative direction, like down or left or backward, and something pushed it or pulled it in the same direction it was already going, it would be a negative acceleration because it's positives and negatives in physics are directions. So you're pulling or pushing it in a negative direction. And since you have a negative velocity and a negative acceleration, it will in fact speed up. So what do you need to know to determine if something's going to speed up? You need to know the direction it's already moving, the direction of its velocity, and the direction the force causing the acceleration is pushing or pulling. If it's the same sign, it's going to speed up. If they're opposite signs, they're going to slow down. Remember, again, in physics, positive and negatives are directions. So if something is moving to the right at 5 meters per second, we'd say that its velocity in the x direction is positive 5. Now let's pretend something comes along and shoves it from behind. Which way is it pushing? Well, if you push from behind, you're going to be pushing it in the same direction it's already going. I would expect it to speed up. Since the object was already moving in a positive direction and something came in and pushed along also in the positive direction, the object should speed up. And that's really all there is to acceleration that I want you to know for now. We're talking about linear acceleration. You want to make sure that you know how to recognize that slope of a velocity time graph is acceleration. You want to make sure that you know that if it's a positive and a positive for acceleration and velocity, it's going to speed up. Negative and negative speed up. Positive and negative is going to slow down. And you're in good shape.